Last time we started this new topic called expanders, or the concept is called expansion. So the theorem that we are proving, and it will take some time to finish the proof, is by AKLLR 1979. So in this theorem we will show that if you are given an undirected graph and vertices S and T, S for source, T for target, you want to check whether there is a path from S to T. Okay, and in fact in the end you will see that you can also output the path, and everything can be done using only logarithmic space in the work tape. Okay, so input size is n, output size is also n, but the workspace is only log n or order log n. And the idea is very simple. The idea is just that you start your random walk from vertex S, which means that whatever neighbors you see, you pick a random one and then proceed. Okay, so obviously the main point here will be calculating the success probability. Okay, so if S and T are in the same connected component, what is the success probability of this random walk reaching T from S in L steps, where L is something like this 300 times n to the 4 log n. So what we have done till now is we defined this normalized adjacency matrix. So normalized adjacency matrix is this 0, 1 matrix, but you will divide by D, where D is the degree of each vertex in the graph. Remember, we have already made our graph regular by a simple transformation. So A is a symmetric stochastic matrix. So it has only real eigenvalues, right? This I left as an exercise. And the maximum eigenvalue is in magnitude 1. Next important thing we defined was the probability vector. So initially the probability vector is all concentrated on the vertex S. So the probability of being there is 1, everywhere else it is 0. And as you take steps, so every step is multiplying A with the probability vector. Okay, this stochastic matrix is the kind of the probability density matrix, and this acts on the probability vector to get a new probability vector, which will be where you will be with what probability after 1 step and 2 step and so on. So we were then looking at this question in red: how large is A to the L times E bar at the Tth place? Okay, so we are interested in the probability of reaching T in L steps. So that is exactly this question: A to the L times E bar, Tth coordinate, and we will study it by eigenvalues and eigenvectors of A. So let's start that study. So first you denote the uniform probability vector which is 1 by n dot dot 1 by n column vector to transpose. So this is we call it the uniform probability vector because this is just equal probability of being anywhere in the graph, which is 1 by n, and this is the ideal. So we want to reach this state, right? So after L steps we want to reach a state wherein probability of being at any vertex is equal, which is 1 by n. This ideal vector we will call 1 bar, and observe that E times 1 bar, this normalized adjacency matrix, is 1 bar. Okay, so what this means is thus 1 is an eigenvalue and 1 bar is eigenvector of A. Okay, this is the first property you learn, and we will also be interested in the vectors that are orthogonal to 1 bar. So, orthogonal means that those real vectors such that inner product of V and 1 bar is 0. So, notice that this means in particular that V has negative coordinates and positive coordinates. So, this is not really a probability vector, it is just a subspace. Okay, this is a subspace, vector space. So, this is called vectors orthogonal to 1 bar. Okay, orthogonal vectors. And one nice property that we will show is the action of A on this subspace 1 bar orthogonal. Okay, that is very nice, and if you look at the maximum length of A V for every V in this space, that will give you the second eigenvalue, which is lambda 2. So, define lambda A to be the max value of length of AV over all the V's in 1 bar and unit vector. So, if you look at the unit vectors in this space and apply A on that, look at the length, pick the maximum length, call it lambda A. This is the second largest eigenvalue. So, why is that? Why is this thing related to lambda 2? In fact, equal to lambda 2. What is the reason? So, this will need a proof. So, first you identify a basis of this subspace. So, pick an orthonormal basis. Let us take B1 to be 1 bar, because that is an eigenvector of A, and then you take B2 and Bn. So, orthonormal basis B1 to Bn such that Bi is, in fact, this is a basis of R to the n. Okay, basically, we are picking n linearly independent vectors, real vectors. The first one is 1 bar, and each of these Bi is an eigenvector, such that Bi is an eigenvector of corresponding to lambda A for all I 1 to n. Okay, so, we have picked this orthonormal basis. So, these are mutually orthogonal, moreover they are unit vectors. they are eigenvectors of A. Okay, this can be found, this exists and it also can be found. It exists mainly because of this above exercise. A is symmetric stochastic, so the eigenvalues are real. And then when you look at the linear system, AV is equal to lambda IV, V will be a real vector. Okay, and then you can also pick them to be mutually orthogonal and unit vector. So this we fix these B1 to Bn, and what happens is then by definition other than 1 bar, so B2 to Bn, if you look at B2, B3 dot dot Bn, they form a orthonormal basis of 1 bar orthogonal. Okay, that's now by construction. So now 1 bar orthogonal is the linear span of B2 to Bn. So which means that any vector V in this space can be written as alpha I bi I equal to 2 dot dot n, and for alpha I real numbers, and now you can study the action of A on this 1 bar orthogonal space. So AV is equal to which is equal to ABI is lambda ABI. So alpha I lambda I is a constant, BI is a vector, so this is the combination of AV, which means what? Now remember that BIs are orthogonal, right? So this is actually a orthogonal, it's a linear combination of orthogonal vectors, so it behaves very well with the Euclidean norm. So if you look at the length of this vector squared, this is exactly equal to alpha I lambda I square. Okay, because BIs are orthogonal and unit vectors, so the length can be expressed as just this sum of squares, which means that so we did not pick V to be a unit vector, but we can make it unit by just dividing by V, length of V square, and that will be alpha I square times lambda I square sigma alpha I square. So we are just taking a convex combination of lambda I squares. Okay. Now when you take this convex combination, or when you take this kind of weighted average, you cannot exceed the maximum. So maximum is lambda 2. Okay, so this A's action on 1 bar orthogonal unit vectors, right, this cannot give a scaling more than lambda 2. Also A B2 is equal to lambda 2. Which implies that A B2 norm divided by B2 norm is equal to lambda 2, right. So what we have is that in 1 bar orthogonal space there is a unit vector whose scaling is exactly lambda 2 by A, and no other vector can exceed scaling of lambda 2. So this overall means that max of AV over unit vectors in 1 bar orthogonal is exactly lambda 2. Okay. So this proves this theorem that lambda A, which was the max scaling, this is exactly lambda 2, and this we are calling lambda A. So lambda A is exactly lambda 2. Okay, this is a very useful property that we have just shown. So we are still just studying eigenvalues of A, right? So next property that we will prove is, remember we wanted to study the action of A to the L. So how do the eigenvalues, and especially the second largest eigenvalue, how does this change as you power A? That's the next property to study. So what we will show is that lambda E to the L is less than equal to lambda A to the L. This is again a cute property. So by definition of lambda, what you know is action of A is limited by this scaling factor for every V in the orthogonal space. Right, we just showed this. The max cannot exceed lambda A. So every action AV divided by V is this lambda A in magnitude. Also, so what we are doing here is that from this inequality we will now study, say, the action of A square. What is A square V? So that we can see as action of A on AV, but then what is AV? So we actually saw in the previous proof that AV remains in 1 bar orthogonal. Okay, so in that sense we can apply this inequality a second time. So formally speaking, this AV is orthogonal to 1 bar. Why? Because inner product is then equal to V comma A 1 bar by symmetry. A 1 bar is 1 bar, and V is by definition orthogonal to 1 bar. So this is 0, right? So this means that AV is in 1 bar orthogonal. Okay, this is a shorter proof than the previous one. So what we have learned is that A maps 1 bar orthogonal to itself. Okay, so A is a map from 1 bar orthogonal to itself, and the good thing about this is then A square is also a map from 1 bar orthogonal to itself, and A to the L as well. And the shrinking that it does, so shrinking each vector by a factor less than equal to lambda A. So if you apply 2 times, it will be square of lambda a, 3 times or L times, then it will be lambda a to the L. Okay, that's the proof. For every V in 1 bar orthogonal. This means that lambda of A to the L is at most this factor that you have shown above. Okay, so this kind of lambda norm of A to the L doesn't exceed Lth power of the norm. That is what we wanted to show. In fact, as an exercise, you can also show that they are equal, but I won't need that. You can show this because basically you look at the eigenvalues of A to the L in terms of lambda 1 to lambda n, and you can show that the eigenvalues are exactly Lth powers of those. Okay, so the order of the eigenvalues that you started with will remain the same. So it's actually a very strong relationship. Powering of a matrix is very nicely related to the original matrix in terms of eigenvectors and eigenvalues. So these were the basic properties of eigenvalues, and now we will go back to questions that are more relevant to the theorem that we want to prove, which is what is the action of A to the L on probability vector. So let's prove it in 2 lemmas. First lemma is for all probability vector, for every probability vector P bar, A to the L P bar A to the L P bar and the uniform probability vector 1 bar. Okay, what is the difference between them? What is the error term? We want to show that the error is small. That is exactly limited by lambda a to the L. Okay, and since lambda a is a fraction, as you walk more and more in a random fashion in the graph, you approach the uniform probability. So the way we will show this is, again we will use this above property of lambda. So we have to see A to the L P bar minus 1 bar as an action of A to the L on some vector. So for that, simply observe that A to the L P bar minus 1 bar, this is actually equal to A to the L times P bar minus 1 bar, right? Because these two vectors are exactly equal. 1 bar is equal to A to the L 1 bar, because 1 bar is equal to A times 1 bar, and then you repeat this L times. And now P bar minus 1 bar is orthogonal to 1 bar. You can show that, and because of that, okay, let's just claim it, and P bar minus 1 bar comma 1 bar is equal to, what is P bar 1 bar and what is 1 bar 1 bar? So remember that P bar is a probability vector, so the inner product with 1 by n will give you overall 1 by n, and the second thing for the same reason 1 by n. So, they are equal, okay, it is 0. So, which means that e to the L is actually acting on a vector which is orthogonal to 1 bar. So, you can use lambda a to the L scaling factor. So, this means that e to the L p bar minus 1 bar. So, let me remove this, this is not needed. So, now e to the L p bar minus 1 bar, this is less than equal to so the scaling factor is maximum this by the previous properties, which again is lambda a to the L, and basically we want to drop this p bar minus 1 bar factor that we are getting. Okay. So, can we drop it? So, we will actually show that this is less than 1. So, we can drop it. So, let us do that. So, define p prime to be p bar minus 1 bar. So, now p prime, if you look at the norm, look at the length squared of p bar. So, p bar is 1 bar and p prime, but notice that p prime and 1 bar are orthogonal as well, right. So, you can write it as sum of squares. So, which means that p prime's length is strictly smaller than that of p bar, right, because this 1 bar's length is positive. So, p prime's length is then strictly smaller than that of p bar, which is, or let me continue using squares. So, length of p bar squared is what? Sigma pi square, right, and pi's are probability. So, you can write it as less than equal to sigma pi, correct. Pi's are fractions, which is equal to 1. So, what we have learnt is that length of p prime is strictly smaller than 1. Okay, so which means that this a to the L p bar minus 1 bar's length is, we have already shown it to be less than equal to lambda a to the L times p prime, which is less than lambda a to the L. Okay, so after L steps of the random walk, the difference between your probability distribution with the uniform probability distribution is lambda to the L. Lambda is a fraction, so it keeps on decreasing. So, you are reaching the uniform distribution. Okay, so, this is a very natural result, but we have obtained it with a great number of calculations and matrix analysis. But there is an easy way to read this, there is an intuitive way. So, what you learn from this, the qualitative reading of this equation is, the further lambda a is from 1, Okay, so in other words, the smaller lambda a is, it's a fraction, but the smaller it is, so the further away it is from 1, the faster is the convergence. To 1 bar, to the uniform distribution. Okay, and this is what motivates spectral gap, the notion of spectral gap. So for a graph like this given by adjacency matrix, normalized adjacency matrix A, the spectral gap is 1 minus lambda a, and we want it to be large. So 1 minus lambda a, or we can equivalently define it for the graph as well in the same way. This is called the spectral gap. Of the graph G. And we wish it large. Okay, so two things we have defined here, two major concepts in spectral graph theory. First is spectral gap, and the larger it is, we want it to be large because the larger it is, expansion in the graph is rapid. Okay, and the reason is this inequality we showed, that after L steps the error term from uniform distribution is lambda to the L. So if lambda is very small, L is large, then this converges very rapidly to 0, okay, making your reachability everywhere with equal chance. Okay, so this is a major point in our understanding, but we are still not done because remember we wanted to fix the value of L in the algorithm, right? So how long should we walk, or how far should we walk? How many times should we pick these random neighbors? So for that actually we have to prove a bound on the spectral gap. Okay, so no matter what graph you are given, because your input is an arbitrary graph, what can you say about the spectral gap? How large is it? So we will show that it is sufficiently large for every graph. That is lemma 2, and then we will be done. So for every deregular connected graph with self loops, in the proof you will see how we will use connectedness and these self loops. Okay, it will appear in some equations, estimates. So for any such graph, spectral gap is sufficiently large, by which I mean greater than equal to 1 over 8 d n cube. So somewhere we should say n is the number of vertices, connected n vertex graph with self loops. Okay, so every vertex has degree the same, which is d, and n vertices, it is connected and there are self loops. Then the spectral gap is 1 over roughly this 1 over n cube. The reason why we are calling it large is because it is inverse polynomially away from 0. So in contrast to this, this spectral gap could have been extremely close to 0, but it is not. Okay, it is inverse polynomially away from 0, so we call it large. It is inverse poly in the input size. That's why we call it large. It's not inverse exponential. It's not 1 over 2 to the n. So this is a good thing. And the proof will be tricky. So first thing we will do is we will replace this lambda g by this as a norm on 1 bar orthogonal space. Okay, so remember that lambda a is the norm, can be thought of as the maximum scaling that, or maximum scaling that you get when a acts on 1 bar orthogonal, right? So we'll use that interpretation. That's the idea. So use the norm interpretation of lambda g when E acts on 1 bar orthogonal. So that's the basic idea, but then you have to do a number of calculations to actually get to this 1 over n cube. Okay, so let us start that. So you can write so let u in 1 bar orthogonal be a unit vector and v be action of A on u, and then we will look at the stretch or the scaling that has happened when you went from u to v. So we will show that 1 minus square of v is large, and once you have shown this, you will get that in other words, we are showing that v bar square is small. So v bar is less than equal to square root of the above. And which is smaller than so this is the sequence of some of the basic kind of landmarks we will have in the proof. We will start with the 1 minus norm of v square. We will show that this is small, and because this is small, norm of v will be smaller than 1 minus 1 over 8 dn cube. Now this will mean that 1 minus norm of v is large. Okay, and 1 minus norm of v is actually 1 minus norm of au, which will exactly tell you about lambda g. So, you will have the statement in lemma 2, fine. So, we will now focus on 1 minus norm of v square for this reason. So, the first claim is that 1 minus norm of v square has a nice expression, okay. It has a nice expression, which is why we actually chose it. So, the expression will be or is Eij times for all ij. Okay, so you can write this 1 minus square as sum of squares with the coefficients being Aij. So, this is called in the literature it is called quadratic form in the Laplacian of G. Okay, so this equation has a fancy name. It is actually related to the Laplacian of the graph. It's a quadratic form in that. Okay, so remember V is AU. So U has n coordinates, V has n coordinates, and what this quadratic form is capturing is it is actually sum of squares for all possible differences across, right? So Ui minus Vj. So this is what we want to show. So once we show this, then the strategy or the plan would be to show that this Ui minus Vj for some I comma j is large. Okay, we will show that for some I comma j it is large, and hence the left hand side is large. That would be the eventual plan. So let us first prove this. So this is just a calculation on the right hand side. So right hand side is sigma Aij times Ui square minus twice Aij Ui Vj plus sigma Aij Vj square, right. Then we will calculate these three terms separately. So this is equal to first term you sum up over I, so you get this. It's basically the ith row sum or sum of the ith row in A, right, minus the second was this Aij Ui Vj. This is the cross term. This is actually related to the inner product Au comma V plus a symmetric thing like the first one. And as you can guess, this will simplify because E is stochastic. So this sigma Aij over J is 1, and then you get sigma Ui square minus sigma Vj square, which is norm of U. What is Au? So this is V comma V plus which is equal to u square minus v square, but u we have assumed to be unit vector, right. So, this is u square is 1. So, 1 minus norm of v square as claimed. Okay, so this is equal to the left hand side. That's all. So now the strategy, as I said, is thus it suffices to show that there exists ij with this ui minus vj square term being large. Okay, one term being large, 1 over 4dn cube. So we will show it next. Here we will use the connectedness and self loops. Okay, we will get this, and once we have 1 over 4dn cube for some term, note that all these terms are actually non-negative. Okay, so the sum cannot be smaller than that. So that will give you the lower bound on 1 minus v square. Right. So remember that we have added, we assume that there are self loops, so we can also focus on ui minus vi. Right. What is happening in those terms? So if there is an I, the self loop term, so ui minus vi square, aii is 1 by d, so you just want this to be more than 1 over 4n cube. So if there is an I, such an I, then you are done already. So the bad case is when for all the i's, this ui minus vi square is less than 1 over 4n cube. This is ui minus vi magnitude is less than 1 over 2 n to the 1.5 for every I. Then we cannot pick these self loop contributions. Then we have to look at edges that are not self loops, right. So there actually we will use connectedness. So what you do is, remember u bar was a unit vector. So let us first sort the coordinates. Sort the coordinates of u. So what you can say is u1 is greater than equal to u2 dot dot un. And we have this information about ui's, that first is that since it's orthogonal to 1 bar, sigma ui is 0. And since it's a unit vector, sigma ui square is 1. So u1, if you look at the magnitude, either u1 is the biggest or un is the biggest, right. So either u1 square is the largest or un square is the largest. So one of them has to be at least 1 by n. just by averaging, because their sum is 1, so one of them has to be at least 1 by n. So what you learn is that either u1 is more than 1 over root n, or un is less than equal to minus 1 over root n. Right, because the sum has to be 0, so for positives there will also be negatives, and you know that u1 is non-negative, and if u1 is positive, then un will be negative. And with the sum of square being 1, you get either u1 bigger than 1 by root n or un smaller than minus 1 by root n. So these are the properties you know. So you know that there is a gap between u1 and un. And the gap is at least 1 over square root n. Right, we have gotten a gap. Let me deduce the following. So there exists an I0 such that ui0 minus ui0 plus 1, this difference, which is non-negative, right, because we have sorted, this difference is at least 1 over n to the 1.5, because between the extremes the difference is 1 by square root n. So there will be some position where the consecutive difference is, difference of the consecutive ui's or ui0s is 1 over n to the 1.5 or more. Again by averaging argument. So now look at vertices 1 to I0. So we wanted this consecutive because we will have some information about u1 to ui0, it's in sorted order, and we will have information from ui0 plus 1 to un, which is again sorted. So look at these two parts in the graph. So 1 to I0 and I0 plus 1 to n. Okay, look at these vertices. This is the whole graph, I mean the vertex set. And since the graph is a connected graph, there will be some way to go from this part to that part, right? It's not disconnected. So there is some edge I to j. There is some bridge between these two connected components. So pick this bridge and look at this cross term in the sum. So there exists an edge I comma j in the graph such that I is in 1 to I0 and j is in so which means that ui is more than ui0, right, and uj is less than ui0 plus 1. So which means in particular that if you look at the difference ui minus uj, this cannot decrease. Okay, so this is a very good thing. We have identified ui uj such that the difference is large and it's an edge. We have identified an edge where the difference is large. Okay, so now just focus on this term. So this means if you look at the term aij ui minus vj square, and then it will be a bit more calculation. So this is greater than equal to 1 by d. So you can write it as some difference of two differences. So ui minus uj minus uj minus vj. Okay, this you can say because this operator's property. Look at this. So the norm of ui minus vj, it's at least the difference of the ui minus vj norm and uj minus vj norm. And then you use the above property in blue. So you will get this is greater than 1 by d. So ui minus uj norm is large, so you use 1 over n to the 1.5. And what do you know about uj minus vj? So the nice thing is that we know, we already assumed something about uj minus vj, which was the self loop thing we did, right? We had assumed that all these ui minus vi's are small. So let's invoke that. That is a useful property. And then square. So which comes out to be 1 over 4 d n cube. Which means that we are almost there, right? So we have shown that in fact 1 minus v norm square is greater than equal to 1 over 4 d n cube. In fact, strictly, because we have shown, and we showed this only by just by using one term, right? So some will possibly be bigger, but cannot be smaller than this, and from which we will deduce by the stretching that A is doing. By that we will deduce something about lambda of A, which is same as lambda of G. Right, that was the original claim. That is what we wanted to show. So 1 minus lambda G is greater than that. So these are all strict. Okay, no. So we have less greater than equal to here. So this will probably, this creates a problem. Oh, I erased too much. Okay, anyway, so the proof is done.